Alright, so here we are with Unit 10, Lesson number 4. And now we're going to take the oxidation reduction or redox reactions to another level. And we're going to look at something called half reactions. And basically what you have to be able to do is after you've assigned oxidation numbers like we did in the previous lessons, what they're going to ask you to do sometimes is then to pull out the oxidation part and the reduction part and write them as two separate half reactions. And you just have to remember a couple of things, and we kind of touched on this earlier. If you take a look at, for example, right here, that's an example of a reduction half reaction. Now, what do you notice about it? Well, two things. Notice that the electrons are on the left-hand side. That's what this is talking about. You should remember that. Also, notice about the oxidation number. Now, since there's no number here, it's obviously 0. The oxidation number went from +3 down to 0. So that is reduction, that is a gain of electrons. So two things, because they will give you half reactions and ask you to identify the reduction half reactions or the oxidation half reactions, so you have to be able to do this. So you always remember two things. The electrons for reduction are always on the left side of the arrow, and the oxidation number has to go down. Now the opposite of that, of course, would be the oxidation half reaction. So if you look at it, here's the same thing, but we just using the same elements, but we've changed it around a little bit. Notice in this case that the electrons are on the, not the left-hand side, but the right-hand side. So that's a mistake right here. The electrons are on the right side, and the oxidation number went from 0 up to a +3. So an increase in oxidation number is oxidation, and that would be Leo. Remember, the electrons are on the right side because they've been lost. So, and this notice here is add electrons to the side of the reaction that has the higher total charge. All you have to remember is if it's reduction, the electrons are on the left side of the arrow. If it's oxidation, the electrons are on the right side of the arrow. That's all you have to remember. So let's take a look at this. And this is a rule, this is something that we already talked about, following the law of conservation, that half reactions, just like a full chemical reaction, must follow the law of conservation of mass, which means there must be the same number of atoms on both sides of the arrow. Not only that, but there also must be a conservation of charge, which means that the gain of electrons during reduction has to equal the loss of electrons during oxidation. And we'll go through and show you what this actually means. So let's go through and show you how to set up or what the rules are for doing half reactions. Now this is a whole bunch of rules, which I kind of think if you just do some examples, you won't even have to worry about these rules. So let's do an example and we'll see how it goes. So if you look at this, they've already started these for you, but you wouldn't have that on a test, right? So let's go through and do the oxidation numbers. We know 0 for magnesium because it's by itself, as is zinc. We know zinc is +2. And we know chlorine's a -1. Magnesium's group 2, it's a +2, and that's a -1. So if we go through this, and this is what I like to do with these lines, the magnesium went from a 0 to a +2. So you know it went up, so that's oxidation. That's the oxidation part of this reaction. So the magnesium started out as 0, it went to a magnesium with a +2, and it lost 2 electrons. Going from 0 to +2 is a loss of 2 electrons. The zinc, on the other hand, went from a +2 down to a 0. So it went from +2 down to 0. Notice the electrons in this case are on the left side. Notice how the electrons are the same. That's what we mean by the law of conservation of mass, right? The law of conservation of charge. That's because the number of electrons lost in oxidation is the same number as gained in reduction. Is it always that simple? Well, of course not, because this is chemistry. But we're going to go with that right now. So let's see what else we got. Okay, here's another example. And I'm not going to probably go through all of them, but all right, this is a synthesis reaction. That's a 0 because it's by itself. That's a 0. Iodine, when it's in a binary compound, is -1. Mercury is going to be a +1. So let's see what happens. The mercury goes from 0 to a +1. So the mercury starts out as 0 and it goes to a plus 1, and it lost 1 electron. If you want to put a 1 in front, that's fine. The iodine, however, goes from a 0 down to a -2. So the iodine goes from a 0, and it goes to iodine with a -1. Now, here's the problem you run into. If you go back and look at the equation, you notice how the iodines are not balanced? That creates sort of a problem because if you remember the law of conservation of mass, there's a way of doing it. You could just balance, sometimes you can just balance the equation, and if you wanted to put a 2 here to balance it, you'd have to put a 2 here. That would certainly balance it. But that would also change this to a 2 and a 2. So here's where it gets complicated. Since each mercury goes from a 0 to a +1, that's 1 electron. But there's 2 mercuries. So the total is 2 electrons, not 1. And also, now that you put a 2 here, that would be a 2 here. So this would also be 2 electrons. Now, do they always end up as both being 2 electrons? Nope, just a coincidence. Okay, let's try the next one. Now, this will give us a chance to work with, as we had talked about earlier, when you have a ternary compound with parentheses, and I'm going to help you to make it a little bit easier. The copper is by itself at 0. The silver is by itself at 0. Now, silver is a +1. And you might say, well, what about the nitrogen and the oxygen? Well, here's what we're going to do. Instead of doing the NO3 separate, we're going to do them together. Okay. How do we figure out what the copper is? Well, that's where that 2 came from. That's actually telling you, if you use the crisscross method, that copper is a +2. I'm ignoring the NO3 because when you have compounds where you have ternary compounds, they're generally going to be spectator ions, which means the N and the O are going to stay the same oxidation number. The oxygen is going to be -2 on both sides, and it looks like the nitrogen is going to be a +5. So, but this only works if you have the same polyatomic ion on both sides. So we can pretty much ignore it. So now we know the copper goes from a 0 to a +2. So the copper starts out as 0, goes to copper with a +2, and that is 2 electrons. The silver starts out as a +1, and it ends up as Ag with a 0. And going from +1 to 0 is only 1 electron. Now here's your problem. Notice how the 2 and the 1 are not the same. They're supposed to be the same. They don't both have to be a 2, but they should be the same number. Now honestly, on the Regents exam, do they care about that? They do not. As long as you write the half reactions correctly, even if the electrons are not the same, they don't care. Well, how would you do that? Well, the only way that you would be able to do that is you'd have to say, well, if I need to get 2 electrons, that means I'd have to start with 2 of these. Because each silver gains an electron. If I have 2 of them, that's a total of 2 electrons. Which means then you would have to go back and put a 2 here and a 2 here. Again, if you get the electrons are not the same, that's fine as long as you get the correct half reactions written correctly. That's all you need to worry about. Okay, and that is it for this lesson.